Whenever an object is experiencing or undergoing translational motion and that object is accelerating, well, that means that a net force must be acting on that object that's creating or causing that acceleration. And this is known as Newton's second law of motion. So it states that the sum of all the forces acting on the object is equal to the product of the object's mass and linear acceleration. Now recall that we defined mass as the inertia of that object, and the higher the inertia is, the higher the mass is, and the higher the tendency of that object to resist its change in motion, to resist that force. Now, I want to ask the following question. Does an analogous concept of inertia exist for angular or rotational motion? In other words, can we find an analogous equation of Newton's second law of motion for angular or rotational motion? So let's begin by recalling the relationship between the net force and our angular acceleration. So recall that if we increase the net torque acting on the object, we increase the angular acceleration. And so that means angular acceleration is directly proportional to our net torque. And because net torque is equal to the net force multiplied by the lever arm, so that means our angular acceleration is also directly proportional to our net force acting on that object. So let's suppose we have a mass m that is being rotated about an axis of rotation by a certain force. Now, the distance between the point mass and the axis of rotation is known as the lever arm, and it's given by this value r. So let's suppose this line is a massless board. It's a mass with negligible mass. Negligible because the mass of this point is much higher than the mass of this board. And suppose that this force is causing our object to rotate in the following circular motion. Now, because the object is moving in circular motion, that means the object has a tangential acceleration that points in the same direction as our force. So recall the formula for tangential acceleration. Tangential linear acceleration is equal to the derivative of the velocity function with respect to time. And recall that velocity is equal to the angular velocity multiplied by our radius of the circle, in this case, the lever arm. So now we simply take our derivative of our angular velocity with respect to time, and that is equal to the instantaneous angular acceleration. So we see that our acceleration tangential is equal to our angular acceleration multiplied by the lever arm. Now, we take this second law of motion, the force is equal to mass times our tangential acceleration, and we replace tangential acceleration with this quantity. So we get our force acting on the object is equal to mass times r, the lever arm, multiplied by our angular acceleration. So now we simply take this entire quantity and represent it in terms of torque. So recall that torque is equal to the force acting on the object multiplied by the lever arm. So we take this entire force and multiply by r, and we get mass multiplied by our lever arm squared multiplied by our angular acceleration. So notice that here we have the linear acceleration, here we have the angular acceleration. Now, this is the inertia, the translational inertia of the object, the mass, but whenever we're dealing with angular or rotational motion, the inertia is given by m times r squared for a point or a particle mass with mass m. So this gives us a direct relationship between the torque and the angular acceleration. So this formula is analogous to this formula for a point particle undergoing rotational motion. Now, the quantity mr squared, once again, represents rotational inertia, which is also known as the moment of inertia of that single mass. Now suppose instead of that single mass, we have a three-dimensional rigid object. How do we find the moment of inertia of a rigid three-dimensional object? Well, we suppose that this object is composed of some number of these point masses. So let's suppose that it has some unknown number, and the way that we find the moment of inertia is we simply take the sum of all these quantities of the individual point particles, point masses. So, for example, ri squared is our moment of inertia of the ith point particle, and we have some unknown number, so we take the sum. And this quantity is known as the moment of inertia, and this is known as I. So we represent the moment of inertia of a rigid three-dimensional object as simply I. So that means the torque is equal to the sum of all these individual moment of inertia multiplied by our angular acceleration, because the angular acceleration for each point particle is exactly the same. So now, because this is a sum, and we replace this sum with simply the letter I, the capital letter I, well then that means the net torque acting on the object is equal to I, our moment of inertia for the rigid object, multiplied by the angular acceleration. And this is the formula for objects rotating, rigid objects rotating about a fixed axis. So in this case, we have the following fixed axis, and it's rotating in the positive direction in the counterclockwise direction. Now, what exactly is the relevance of this law? What does this law mean? Well, this law means the following. Let's suppose we have two rigid objects, rigid cylinders, that have the same exact mass. So we have this rigid cylinder with mass m, and this rigid cylinder with the same exact mass m. Now notice, our diameter of this object is much higher than the diameter of this object. And what that means, according to this formula, because the r is much greater for this object than this object will have a much higher moment of inertia. And so that means it will be much more difficult to make it rotate, and it will be much more difficult to stop it from rotating than this object. In the same way that if we have a translating object with a very high mass, it has a very high inertia, and so it will be very difficult to stop that object because of that very high inertia.